Okay, so next up, while he's setting up, is Carsten Baum, who is a postdoc in Aarhus here. And Carsten is going to be talking about a work that has a special place close to my heart, as you may see when his slides come up, which is efficient constant round MPC with identifiable abort and public verifiability. Or over to you to read out the alternate title if you like, Carsten.
Fair enough. Can you hear me?
Yep. So good.
Great, fantastic. Yeah. So this is a joint work with Emanuela, Peter, and Eduardo. And yeah, so this work is about MPC with identifiable abort, or how to spot a bad party in MPC like a boss. And so the boss you get if you look at the last names of each of us and look at the first character of these, then you may get where this abbreviation comes from. So this is TPMPC, so I'm not going to talk about what is MPC. I'm just going to motivate why our work is interesting. So one application that one sometimes sees for MPC is sealed bid auctions. So if you want to implement a sealed bid auction, what you have is you have parties that have an input, right, which is, for example, a certain amount of money, and they want to have an auction where they find out what is the highest bid, and then some good goes to the highest bid, right? So they send this to some trusted third party, and a trusted third party is going to compute the function what is the highest bid, and is then going to output to everyone Alice had the highest bid, and Alice bid so and so much money in this. So okay, multi-party computation has correctness, it has privacy, which is fantastic for this application, right? Because due to correctness, it computes the right output, which is Alice had the highest bid, and it also is private in the sense that all the lower bids are going to be kept secret. So that is great, but it does not have fairness. Namely, for certain settings, fairness is possible, but Cleve showed in 1986 that if you have a dishonest majority setting, then fairness is not achievable. In particular, that includes the two-party setting. So if you have a two-party computation, then it's not going to be possible to have a fair such two-party computation. And fairness here means that if the dishonest party gets the output, then the honest party gets the output too. So in that sense, if the protocol is unfair in our setting here, that would mean that Alice and Bob, for example, would never see that Alice won, whereas the adversary knew that Alice provided the highest bid, and it was 4 bags of money. Right. So why is this a problem in auction? So if you look at the recent years of MPC literature, which mostly were unfair protocols, then it just said that if the protocol fails, then you just rerun your protocol, right? And it's going to be fine. So no problem is if you rerun an auction and the adversary know what was the highest bid of an honest party, then the next time the adversary can simply increase his bid by whatever Alice bid +1. So, he's going to be able to cheat in that setting. And obviously, if you have multiple MPC instances and you don't guarantee input consistency between these MPC instances, then you're going to get there, right? Okay, so how to solve this? So fairness is not possible. One solution here would be, as I said, input consistency between multiple MPC instances, but what other solutions are there possible? And one solution is called identifiable abort. Now, an identifiable abort, if everything goes well, then we see the same as before. Namely, you run the computation and you get the outputs, and that is fine. But in difference to an unfair protocol, we now have that if the adversary cheats, he gets the output. The honest parties are not guaranteed to get the output, but the honest parties are at least going to learn the identity of at least one dishonest party, right? That means, and all of them are going to agree that this party is dishonest. So if they rerun the protocol, they can exclude dishonest parties from the computation. And this way, if this, for example, was the only dishonest party, then this way we would have a guarantee that the next round is going to be run honestly. And then also these identifiable protocols could be leveraged in other ways to, for example, punish cheaters. And so there's other literature in this area that's interesting. So, and the cool thing is, in comparison to unfair protocols, in comparison to fairness, we know that identifiable abort is a property that we can get in the dishonest majority setting. For example, you can tweak GMW to have this property, and there was this work in 2014 by Ishai et al., where they showed how to achieve this with adaptive OT. So our contributions in this area are, so we construct an actively secure MPC protocol that has identifiable abort and is running in a constant number of rounds. In particular, so it's leveraging a BMR style protocol to achieve this. And it's secure against a static adversary controlling a dishonest majority. Moreover, it has a reasonable overhead over state-of-the-art constant round MPC that doesn't have identifiable abort. So it achieves, it hopefully in an implementation could achieve a similar efficiency. And in our work, we also show that you can achieve public verifiability of the output or public verifiability of the identity of the cheater in our construction if you use a bulletin board, such as, for example, a blockchain in this setting. But in this talk, due to the lack of time, I'm only going to talk about identifiable abort and not how to get to the public verifiability setting. As I want to mention that we're not the first to talk about identifiable abort. So as said before, this gained interest in 2014 with this work of Ishai et al., where they provide a GMW style compiler for constructing an MPC with identifiable abort. So a disadvantage of their work is, since it's a compiler, you could also take a constant round MPC protocol and just throw the compiler on top. But the problem is, first of all, it needs adaptive OT, which is a costly primitive. So running adaptive OT or adaptive OT extension is going to be very costly to implement. And second, doing that, applying this compiler black box would mean that you would have to prove in zero knowledge that you gobbled the circuit correctly. And this is something that you most definitely don't want to do because it's going to be highly costly. So Kiayas et al. Gave a transformation also of this to the public verifiability setting, where they then use NISX to compile the original protocol, but also that is going to be rather inefficient in practice because you would then have to prove in zero knowledge, prove with NISX that you gobbled the circuit correctly. So it's just going to add some overhead on top. So there has been work concerning efficient MPC with identifiable abort. So this is work by myself, Emanuela, and Peter from 2016, and concurrent work by Fair and Spini, as well as Cunningham, Fuller, and Yakubov, who, and we're like, all of these protocols have in common that they construct a IDMPC that where the round complexity scales with the size of the circuit. And they're all kind of built on top of speeds, and they all have also the disadvantage that they require a large field to actually run, whereas our construction that I'm going to talk about can be instantiated over F2. So first, let me mention this IOZ14 compiler, because we're going to need that a bit later to explain why our construction is secure. So how do Ishai et al. Achieve identifiable abort? So as I said, so they take a protocol. Let's assume this protocol is in the online model, and then we're going to add some preprocessing to it. So what's going to happen in the preprocessing? So their observation was that the preprocessing is as such input independent. So if something goes wrong, we can just open the preprocessing and work with that, right? So how does this help for identifiable abort? Well, first, parties will commit to the random tape that they're going to use throughout the whole protocol. Next, they're going to generate some correlated randomness using the adaptive OT as mentioned. And basically what they're doing is they're going to preprocess some zero knowledge proofs such that they can then later in the online phase, when they run the actual protocol, use this preprocessed data to prove statements about the next message function efficiently. And then in the preprocessing, they run all the communication through a broadcast channel. So this way you can always see if a party never sent a certain message. And then how does this achieve identifiable abort? Well, if somebody complains that something went wrong, all you do is you open the commitment to your randomness tape. That's fine because, as I mentioned, it's preprocessing is input independent. It doesn't cost you anything. And then each party just simulates all the parties in their head and what they should have done based on this randomness tape and compare with the messages sent. And since they all ran over this broadcast channel, that's going to be fine. And this way you identify a cheater, or if the whole transcript was correct, you identify whoever issued the complaint as the cheater. Right? And then once this is finished, you know that you have all the preprocessed data that you need in order to run the zero knowledge proofs. And if you can do these zero knowledge proofs in the online phase, then, I mean, you trivially get identifiable abort, right? Either a message was sent, and then if it was sent, it's consistent due to the zero knowledge proof. So there's, and you can identify cheaters based on that. So that's rather straightforward. So for our construction, since we want to get MPC in constant rounds, let's start with garbled circuits, because the way how we're going to get to constant rounds is by using garbled circuits. And so how does garbling work for, let's say, passive two-party computation? Well, there's Alice and there's Bob, and Alice takes the circuit and throws it into an algorithm which is called garble, and that's going to output a version of the circuit that is very unintelligible. So Bob, if you only give him the circuit, he has no idea what the circuit there is doing. And in addition, Alice provides an input encoding function that allows her to encode her input, and also allows Bob to encode his input interactively. Once Bob has these two encodings, then the evaluation algorithm guarantees for Bob to get the correct output of this computation, which is C applied to x1 and x2. And at the same time, the garbling does ensure that all that Bob learns is actually C applied to x1 and x2 and nothing else, right? And if you want to have both parties to get the output, then Bob would have to send the output back. So how does this work in a multi-party setting? So if we have multiple parties, we can't just have one party who garbles the circuits, because, you know, then we basically want each party to do the evaluation. So no party as such could be the garbler, because then it would have all information necessary to get the inputs of the other parties, and that would be bad. So instead, the garbling and the input encoding would be run in a generic MPC protocol. And so this is gonna happen in some pre-processing phase. Parties are gonna input some Boolean circuits into the garbling, and out comes the garbled circuit plus some possible error. And the possible error is due to the fact that we want to have an efficient garbling step. And then they also input their inputs into the MPC, get a garbled version of the inputs, and then each party can locally evaluate. So if then each party broadcasts its input encoding, then we can apply the circuit to the input encoding locally using the evaluation algorithm. And the guarantee is that if the error is 0, so the circuit was garbled correctly, then we get the correct output. And in normal BMR protocols, you otherwise would abort, right? So our goal is going to be, how can we tweak this to instead have cheater identification? So the first thought would be, why don't we just compile this HSS17, this BMR protocol with the IOZ compiler? So first of all, we would put a preprocessing before the preprocessing, so it doesn't really make sense. The actual BMR protocol already has a circuit, an input independent preprocessing phase. So why would we run this with all these zero knowledge proofs on top? It doesn't really makes sense. And second, as I mentioned before, garbling actually means locally evaluating PRFs, and this is very inefficient in zero knowledge, because now we would have to prove in zero knowledge for each gate that you're garbling correctly. And since each party has n PRF calls to garble a gate, and there are n parties, so you'd have to generate O of n squared zero knowledge proofs just to show that one single gate was garbled correctly. This is going to be an insane overhead in practice, so we don't want to have this. Our solution instead will work without no zero knowledge proofs at all, and I'm going to explain to you how that works. So in order to explain how it actually works, let me recap how to garble an AND gate in YAO. So in the two-party settings, you have input keys and you have output keys, and so normally an AND gate would have an input bits or output bits, and the idea, the great idea that YAO had was you can actually replace, you can logically replace the bit with a bit string, and then you can instead encrypt the truth table by, let's say, replacing the output bit string with an encryption under the input bit strings. So this way, you would, for example, for the 0 key, you would encrypt this, would encrypt this 0 key whenever you would get 0 as the output of the input bits logically, right? If the input bits are 1 and 0, then the end of this is 0. So you should, in the table, place an encryption of the 0 key, and the same then for the 1 key. And then in addition, you need to shuffle this, because otherwise the evaluator can see where the encryption worked and thereby guess what the truth of the bit was. So this is the standard trick of how you do this for a two-party setting. If you go for the multi-party setting, then the HSS paper and also other constructions do the following. Instead of so they still encrypt a whole key, but instead of this key being, let's say, 128-bit, or if we listen to Xiao from the last talk, hopefully a bit longer, instead each of these are going to be some contributions that come from all of the parties. So let's say the first party contributes 128 bits, the second party contributes 128 bits. So the encryption itself will be an encryption of all of these concatenated under, but still under the whole input key. And there, observe that once we decrypt, we will have that each party locally knows at least one of these blocks. So party I will know K0 and K1, right? And how does this encryption work? So so we'll have that these are, as I mentioned, so in the encryption of the concatenation is going to be a concatenation of encryption. So we basically encrypt the first string, the first chunk, so the output wire of the output key of the first party under the input keys, and then the second, and so on and so forth. So now during evaluation, what actually happens is that each party has as the same as before in YAO. So each party has the input, let's say, has U and V as input keys, and it's going to use this to decrypt block by block each of these encryptions. So it's gonna know where to look at in the table using point and permute. I'm not going to go into detail how that works. It's going to know where to look at in the table. It's going to take the encryption, and the guarantee is that it can only decrypt this encryption. It's going to get the correct output key, or it's going to first decrypt the first party's output key, the second party's output key, and so on and so forth. So what does that, so yeah, and as I mentioned, that this is what each party actually does locally. So each party has the whole KUA, it has the whole KVB, and it's going to do the exact same thing here, and then it's going to continue with the evaluation with the next gate. But it's only going to do so if it finds that its 0 or its 1 key was in the decryption. As I mentioned, each of the parties contributes one chunk of this key, and so in the decryption it should see either the 0 or the 1 key appearing there. And if it doesn't, then something must have gone wrong. So in HSS, this is how you normally find out that that somebody did the wrong garbling, and then you would abort. So our observation is that this garbling is done from shares that each of the parties has. And then the parties this way generate shares of an encryption of the output key, or of a row in a garbled gate. And then the parties broadcast this. So and actually during the decryption, correct decryption, the parties would learn these keys here already, and they during the garbling already learn the shares of this value here. So if we redo, so all in all the parties will actually reveal in a correct evaluation are all the values that are necessary to redo the garbling step, right? So that means that that all we need to do is to basically during the pre-processing or leaving pre-processing out, all we need to do is to redo the garbling step in public made on consistent data. And once this is done, we will know if the gate was garbled or not. So if some party complains this gate was not garbled correctly, we can actually just redo the garbling step in public and figure out if this party's claim was true or not. So yeah, all we actually need to do is we must make the pre-processing output commitments to these shares that are used in the garbling step. And then if some complaints are raised about the garbling being wrong, then all that is necessary is to open these shares. So yeah, how do we then get this from the preprocessing? So then we're going to modify the preprocessing of the HSS paper, where like mix it together with the IOZ compiler, in the sense that parties again commit to their random tape, then they run the preprocessing as in BMR, as in HSS, but additionally they generate commitments. And this is run through a broadcast channel. They're going to check the consistency of the commitments that they generate. And in the end, if there's any inconsistency, they're just going to open the commitments to the random tapes and compare what they did, that the messages that they sent were generated correctly. And it turns out that the overhead of doing this is actually not that big, and we quantify how much it is in our paper. So before I wrap up, let me just mention one problem that this actually has. Namely, if you simulate, if you want to prove that this thing is secure, this construction is secure, you need to prove this for the preprocessing. Now, if everything goes fine in the preprocessing, the simulation strategy is going to be okay. But if your preprocessing aborts, then your ideal functionality is going to output the actual material that the honest parties got, because this is what verification is about, right? You see from the ideal functionality what shares the honest parties got, but you simulated before a transcript not knowing what the honest parties would actually be getting. So your choice of randomness tape in the simulation is going to be inconsistent with the ideal functionality. So in IOZ, they solved this problem by using adaptive primitives, and then you can easily equivocate. But as I mentioned, it's going to be very inefficient. And our solution is to define the problem away. And we do this by realizing that once we know that the preprocessing is done correct, you actually don't have to reveal your outputs of honest parties anymore. Why? Because I mean, if the whole protocol gives you something consistent, then everything must be correct. So there's no reason to abort. And if you abort before that, then the honest parties don't already have their outputs of the ideal functionality. So that means that your ideal functionality doesn't have to reveal these outputs already, and there's no reason to equivocate. I just want to mention that there is an alternative to doing this in some recent work of myself, David and Dowsley, where we show that you can also avoid these problems by a special type of simulation for verifiability, which we call Uber simulation. And yeah, that paper is also currently in submission. So just to wrap up, in our work, we construct an efficient constant run MPC with identifiable abort and also public verifiability. As mentioned, so the theoretical challenges are to deal with this identifiable abort property and the public verifiability, and to eliminate this need for adaptively secure preprocessing that the IOZ approach had, and we solved this in our work. And our overhead over the existing HSS17 paper is that in the online phase, we need to use a bit more broadcast, but even that we can optimize away by using an optimistic approach where the parties first optimistically run the protocol, and only if they sense that something goes wrong, they have to actually make use of the expensive broadcast. And in the offline phase, we have to add these homomorphic commitments, and we explain in our paper in detail how much overhead you actually get from that. The good thing is that we can actually use very cheap homomorphic commitments that can be constructed from symmetric primitives only. So this is not going to give you any public key crypto that you have to throw on top. And with this, I'd like to end my presentation, and I'm open for questions.